Hello viewers, continuing with our series on continuity and differentiability. So far in our chapter on continuity and differentiability, we have covered number of techniques of finding derivative of a given function. Today we will be discussing what is called as the second order derivative and also a significant theorem in calculus known as the mean value theorem. So, what does it mean by saying second order derivative? What you have done so far were first order derivative. Given a function, find the derivative, it is the first order derivative. Suppose I take a polynomial function as x cube plus 3x square minus 5x plus 7. We know that its derivative is nothing but a second degree polynomial. In this case 3x square plus 6x minus 5. It is again a function of x. So, I can always differentiate it with respect to x. So, derivative of f dash x is going to be 6x plus 6, which is what is called as the second order derivative of the given function. We also use alternative notations as f double dash of x. So, first derivative is read as f dash x or f prime x, the second order derivative as f double dash of x, and if I call y as my f of x, then the second order derivative is also read as d2y by dx square, not same as dy by dx whole square. So, it is a notational use of this square as it is being written here. So, note and read it correctly so that you do not misuse it. Let us take a function. Suppose I have tan inverse x or I have exponential x into cos of 3x. Can I find the second order derivative? So, starting with y as tan inverse x, dy by dx is 1 by 1 plus x square. Therefore, the second order derivative will be the derivative of 1 by 1 plus x square, which is nothing but minus 2x by 1 plus x square whole square. And where did I get that from? Using the quotient rule, because I have 1 by 1 plus x square. As simple as that. Take also a minute to understand what exactly does the second order derivative mean. The first order derivative was the instantaneous rate of change, and now I am finding the rate of change of the rate of change. Have you come across any quantity where you have used this? If you try to recollect, the derivative of a given function represents in physical interpretation velocity, and the rate of change of velocity would be acceleration. So, these are quantities which you are familiar with, and therefore, second order derivative is also a very significant concept. What happens if I have exponential x into cos of 3x? Not much would change. Let us take a look. If y is exponential x cos 3x, the first derivative using the product rule turns out to be exponential cos 3x plus exponential x into negative 3 times sin 3x, which I may write as exponential x into cos of 3x minus 3 sin 3x. Now, again differentiating this function, I need to be careful that I am using product rule. So, I have now differentiated exponential x, kept the second term as it is, whereas in the second place I have now differentiated cos of 3x minus 3 sin 3x exponential x as it was. What you really just need to do is simplify it a little if possible, and that would be your final answer. Another possible application, one of the very usual questions that you come across would be where the function y and x are not related directly to each other as an explicit function or an implicit, but they are related through a parameter, and you are asked to find the second order derivative. There is something very significant to be learned here, so keep a close watch. To find the second order derivative, I definitely need the first order, and we have an understanding that dy by dx is derivative of y with respect to theta divided by derivative of x with respect to theta. So, let us get up to that point, starting with dy by d theta and dx by d theta using the chain rule. Taking the quotient, I get derivative of y with respect to x as minus cot theta, and this is a point where you need to be now careful. I want to find the second order derivative of y, which means that I have to find the derivative of the derivative of y with respect to x, but dy by dx is a function of theta, not x. So, also at the same time x is a function of theta. I need to find d2y by dx square. So, what I can do is take z as dy by dx, so that d2y by dx square becomes dz by dx. Z is a function of theta, x is a function of theta. Therefore, dz by dx is dz by d theta divided by dx by d theta using the derivative of parametric functions, which results in nothing but cosec square theta, derivative of minus cot theta, and derivative of a cos cube theta in the denominator. Simplifies to cosec cube theta divided by negative 3a cos square theta. Now, the question asks you to find the second order derivative at theta equal to pi by 4, which simply means that plug in the value of theta as pi by 4 and evaluate. In this case, the value turns out to be minus 4 root 2 upon 3a. Let us take another application of the second order derivatives, one of the very usually tested question in the board exams. It says, if y is square of sin inverse x, prove that. So, you have to get this expression which involves the first derivative and the second order derivative as well. So, you have to prove that 1 minus x square d2y by dx square minus x dy by dx minus 2 is equal to 0. Starting with y as sin inverse x whole square, using chain rule, I get the derivative of y with respect to x as 2 sin inverse x by under root 1 minus x square. Now, in most of these questions, the tendency is to mechanically start off with the second order derivative, that is, differentiate this function as it stands, which would mean that you will need quotient rule and chain rule again, because you have a root of 1 minus x square. And then possibly what would one do? Plug in the value of dy by dx and d2y by dx square and show that entire expression that you are given equals 0. I am going to suggest you an alternative, a much more efficient method. Take a note of that. Instead of finding the derivative of this function as it is, what I do is I cross multiply with root 1 minus x square and then square both the sides. Once I have done that, notice the right hand side is actually nothing but 4 times y. So, it is already a much more simplified expression. Differentiating with respect to x on both the sides and taking a note that the derivative on the left side needs product rule and derivative of dy by dx will be d2y by dx square, derivative of square of dy by dx will be 2 dy by dx into d2y by dx square using the chain rule. What is left is just a simplification, divide by negative 2 times dy by dx and you get your required expression. This is a definitely better alternative to what you have possibly thought of by doing the differentiation directly and then verifying the expression. Let us now consider the mean value theorem, and to begin with we are looking at Rolle's theorem, which is actually a particular case of mean value theorem. The Rolle's theorem states if a function f defined on a closed interval a b is such that it is continuous on the closed interval a b, it is derivable on the open interval a b, and f of a is equal to f of b, then there exists at least one value c of x in the open interval a b such that f dash of c is equal to 0. Now, this theorem is a significant result, and the best way to understand this would be to look at its geometric interpretation and then see how simple this result is. What it says here is that if I have a curve which is continuous, in this case this orange curve represents our function f of x. It is a continuous graph, there is no break, no gap in the curve. Derivable in the open interval a b would mean that I can draw tangents at every point of that open interval. The third condition, f of a is equal to f of b. That means the function starts and ends at the same height from the x axis. And if all these three conditions are satisfied, then between a and b there must exist at least one c at which we are looking at something special happening. And what you see in this case is that there exists at least one c between a and b at which the curve is turning, and at these points the tangent will be parallel to x axis. And if tangent is parallel to x axis, the slope would be 0, and that is exactly what we mean by f dash of c is equal to 0. So, if a function is continuous in the closed interval, derivable in open interval, f of a equal to f of b, it starts and stops at the same height from x axis, then there is always at least one point between a and b at which the tangent will be parallel to the x axis. Now, the mean value theorem is a more general result. Mean value theorem says that if a function f defined on a closed interval a b is such that it is continuous on the closed interval a b and it is derivable on open interval a b, just these two conditions, then there exists at least one c in the open interval a b such that f dash of c equals this quotient, which is f b minus f a by b minus a. Again, just as in the Rolle's theorem, here as well, if you see the geometric interpretation of this theorem, the things would get much more simplified and meaningful. Note that mean value theorem conditions differ from Rolle's only with the understanding of there is no requirement of f of a to be equal to f of b, and when f of a is equal to f of b, f dash c would be 0. So, that is what I meant by saying that Rolle's theorem is a particular case of mean value theorem. Now, what does this theorem geometrically signifies? Here I have a graph of a curve, in this case the red curve representing function f, which is continuous, no break, no gaps, derivable in the open interval. So, tangents can be drawn at any point, and what the theorem's conclusion was that between a and b there exists at least one point, in this picture the point c, at which if you notice the slope of the tangent equals the slope of the chord AB. And so, if you look at our result, which is f dash c is equal to f b minus f a by b minus a, it is nothing but our good old result of y 2 minus y 1 by x 2 minus x 1, slope of the segment joining the 2 points a and b. So, the result signifies that between a and b there exists a point at which the tangent is always equal to the secant which is joining the end points of the domain of the curve. and that is what the mean value theorem is. What you are required to do along with knowing the theorem and geometric interpretation is verify. How do I, given a function, verify whether mean theorem is applicable or not? So, now that you have seen the geometric interpretation of Rolle's and mean value theorem, I hope the theorem, which is so fundamental and so significant, has become so meaningful for all of you. Do take up problems where we have to check, verify whether the theorem is applicable or not. That is, if one of the conditions fail, theorem is not applicable, right? See you in our future series. Goodbye.